Hello everyone. We would like to introduce our paper, titled Crosshead Knowledge Distillation for Object Detection. Now, let's start from the introduction of this paper. Knowledge distillation has been deeply studied in object detection. Existing KD methods can be roughly classified into two categories: prediction mimicking and feature imitation. Feature imitation, typically like PKD, argues that intermediate features contain more information than the predictions from the teacher. It aims to enforce the feature consistency between the teacher-student pair. Differently, prediction mimicking points out that the smooth distribution of the teacher's predictions is more comfortable for the student to learn than the direct distribution of the GTs. Thus, it forces the student to resemble the teacher's prediction distribution. Prediction mimicking plays a vital role in distilling object detection models, but it has been observed to be inefficient than feature imitation for a long time. Despite just catching up with the advanced feature imitation methods, LD shows that prediction mimicking can transfer task-specific knowledge. This motivates us to further improve prediction mimicking. Through investigation, we observe that prediction mimicking may suffer from a conflict between the GTs from the student's assigner and the distillation targets from the teacher. As a result, the student detector experiences a contradictory learning process during distillation, which seriously interferes with optimization. To quantitatively measure the degree of target conflict, we statistic the ratios of conflict areas to the positive areas in the COCO dataset, which demonstrates the target conflict is quite common in object detection distillation. To alleviate this problem, we present a crosshead knowledge distillation pipeline, abbreviated as CrossKD. The overall framework is illustrated in the above figure. Like many previous prediction mimicking methods, our CrossKD performs the distillation process on the predictions. Differently, it delivers the intermediate features of the student to the teacher's detection head and generates crosshead predictions. Then, the KD operations can be conducted between the new crosshead predictions and the teacher's predictions. This operations can bring the following advantages. First, the detection loss and the distillation loss are separately applied to different branches, alleviating the conflict problem, resulting in a better optimization towards GTs. Second, as mimicking the teacher's predictions is the target of KD, it can offer more task-oriented information compared with feature imitation. The objectives of CrossKD are a combination of the original detection losses and additional distillation losses. About distillation losses, we apply different distance functions to transfer task-specific information in different branches. We also test other crosshead strategies, illustrated in the above figure. As presented in the above table, strategy B significantly lowers than CrossKD. We hypothesize that this may be attributed to the suboptimal optimization of the student's blocks in the early training phase. Strategy C and D still perform both distillation and detection losses at the student's detection heads, so that the target conflict problem still exists. Moreover, these strategies also have limited impact on the student's backbones. Finally, we conduct extensive experiments on COCO dataset to investigate the effectiveness of our method. We first compare our CrossKD with SOTA methods in the left table. CrossKD outperforms all other methods without bells and whistles. To demonstrate its generalization, we also apply CrossKD on different detectors in the top left table. All results outperform the original teachers. Furthermore, we perform prediction mimicking in our CrossKD between detectors with different assigners to explore its effectiveness against the target conflict problem. We visualize the statistical variation during training to conduct further analysis on CrossKD and prediction mimicking. We calculate the L1 distances between the teacher and student predictions. As plotted in the above figures, the student's predictions is relatively close to GT's, demonstrating CrossKD can relieve the rigid hard imitation between the teacher and student predictions. Moreover, we also visualize the gradients on the latent features of the detection head, as shown in the above figure. As illustrated, the gradients generated by PKD have a large and wide impact on the entire feature maps, which is inefficient and not targeted. On the contrary, the gradients generated by CrossKD can focus on potential semantic areas with objects of interest. For more details, please refer to our codes.